This is the first video for section 3.4, Annuities and Sinking Funds. In this video, we will cover the following objectives. We will calculate both the future and present value of an ordinary annuity and an annuity due. Before we begin, some definitions. An annuity is an account for investing money at regular intervals throughout the length of the account. Interest is also compounded at regular intervals throughout the length of the account. So an annuity contrasts from a regular savings account in that an individual does not need to have a large lump sum of money at one time to start an annuity. So the way a traditional savings account works is an individual has a large lump sum of money to invest and then lets that money gain interest. This is not practical. Many people have a small amount of money every month or every few months to invest. And then an annuity is really the best type of investment for that. An annuity in which the repeated investment is made at the end of the compounding period is an ordinary annuity. An annuity in which the repeated investment is made at the beginning of the compounding period is an annuity due. The sum of all payments and interest that accumulated over the length of the investment is called the future value of an annuity. In Figure 1, you will see summarized all of the quantities we're working with, together with their variable names and together with some details about those. Many of these variables are as introduced before. The interest I, the interest rate R, the principal P, the time T, and the amount A. These are all as in previous sections. The new variables here are capital R. Capital R is the regular payment, the number of compounds per year. Common values of M are annually, so that's 1 compound per year. Quarterly, so that's 4 compounds per year. Monthly is 12 compounds per year, or daily is 365. And then N is the total number of compounding periods that's found by taking M times T. So here's two formulas, the future value of an ordinary annuity and the future value of an annuity due. You'll notice some similarities to these formulas and some differences. Those differences all come from is the investment made at the beginning of the compounding period or the end, right? That just makes a difference in how interest accumulates for that account. Example 1. Use the appropriate future value of an annuity formula and the given variables to solve for the missing value. Round to the nearest cent. So we're told that the regular payment is $400. The interest rate is 0.8%. The number of compounds per year is 12, and there's 48 total compounds. Payments are made at the beginning of the compounding period. That points me to which formula I'd like to use, which is this formula here. That's supposed to be an M. Okay, so once choosing the correct formula, the next step is plug in all of the variables you're told. So we're told that the regular payment is $400. The interest rate is 0.8%, which as a decimal is 0.008. There's 12 compounds per year, and there's 48 total compounds. Now I'm going to write 49 up here in the exponent because I see the exponent is 48 plus 1. Okay, so once you plug in the appropriate values, then we can follow your order of operations. So order of operations specify that I start inside the parentheses with my simplifying. So starting inside the parentheses gives this 0.008 divided by 12. That gives a result of 0.00667. Now, when you are doing these calculations, it is best to include as many decimal points as you can in intermediate steps, and then round when you get to the very last step. For practicality in intermediate steps here, we are writing down just 6 places after the decimal point. So all of this to the 49th power. And then again in the denominator, the 0.008 divided by 12 becomes 0.000667. Okay, so after this, still inside those parentheses, I can add 1. After this, we can go ahead and evaluate the exponent. We can take 1.000667 to the 49th power, and that gives a result of 1.033195. Again, in these intermediate steps, it is best to include as many places after the decimal point as you can and wait until the very end to round. Okay, at this point, I can go ahead and do that subtraction in the numerator. So I can take 1.033195 minus 1. Next, I will go ahead and perform this multiplication and division. So in one step, I will take 400 times 0.033195, and then I will divide by 0.000667. So doing that gives a result of 19,916.900640 minus 400. And then the last step is to do that subtraction. So doing that subtraction gives a future value of $19,516.90. At this point, you can round to the nearest cent. So that gives the future value on the account. Now, a quick check I like to do is I will say, okay, the regular payment was $400, and I made 48 of those regular payments. So altogether, I had $19,200 invested in this account over the length of the account. Now, the future value of the account is $19,500. So this quick check just shows me that my future value of $19,516.90 is feasible, right? It makes sense that with a principal of $19,200, I would have about $300 of interest extra. Now, this quick check is not perfect, right? But it's just a quick way to see if your answer is even in the realm of what could make sense. Okay, moving forward to example 2. First, a definition. Sinking funds. A sinking fund is an account in which money is invested and interest is compounded at multiple regular intervals to fund a future purchase of a known amount. With a sinking fund, the regular investment amount is unknown. A sinking fund is essentially an annuity where you know how much money you want in the future, and the question becomes, how much money should I invest every month or every quarter to make it to that future amount? So in this text, all sinking funds will be solved with the ordinary annuity formula. Example 2. Use the appropriate future value of an annuity formula and the given variables to solve for the missing value. Round to the nearest cent. So we're told the interest rate is 1.8%. The time is 2 years. The number of compounds per year is 12. And the future amount is $2,478.95. So my first step is to choose the appropriate formula. And the appropriate formula is this one here. And then the next step after that is to plug everything in. So we're told the future value is $2,478.95. We are searching for the regular payment. We're told the interest rate is 1.8%. I'll go ahead and write that as a decimal. We're told there's 12 compounds per year. Now, off to the side somewhere, I'm going to do a calculation to find n, because I am not told n, the total number of compounds. But I'm told that interest is compounded 12 times per year, and that I'm investing for 2 years. So there's 24 total compounds. Okay. At this point, it's simplifying a little bit and then solving for r. So to begin my simplifying here, I will start with what's in the parentheses. So starting inside these parentheses, I get 0.018 divided by 12 gives 0.0015. And same thing in the denominator, 0.0015. The next thing I can do is go ahead and add 1 in the numerator. So adding 1 gives 1.0015. Then we can go ahead and evaluate that exponent. So evaluating the exponent gives 1.036628. Next, I can subtract 1 in the numerator. So subtracting 1 in the numerator gives 0.036628. Next, I can perform that division. So at this point, you can perform this division here. That leaves $2,478.95 equals your regular payment times 24.418590. And now we want to solve for r, right? So at this point, our simplifying is done. And now we are solving this equation for r. So you can divide both sides by 24.418590. Divide this side by 24.418590. And doing that division gives a result. And at this point, I'm going to round to the nearest cent. So 101.52, $101.52 is your regular payment. Again, I have a quick check that I like to do. It is not a perfect check, but it lets me know if this answer is in the realm of reasonable. So my quick check will be a regular payment of $101.52 times 24 payments total. So that would mean I invested $2,436.48 total. So now I would compare that number to the future value of $2,478.95. And I would say, all right, well, an accumulated interest of $40 or so, that seems feasible, right? A couple red flags would be if this number were way smaller than 2,400 something, or if this number were bigger than $2,478.95, right? Both of those would be a red flag that my regular payment maybe isn't correct. But this looks like a likely amount for my amount invested to then have my future amount be as the problem stated. This concludes example 2, and this concludes video 1.